All right. So we're in section 14.2. So what we're going to do today is we're going to extend the ideas that we've been talking about with multiple integration to talk about integrating over a region in the xy plane, but we're going to add a function, so some kind of surface that's above the xyz plane. Sorry, the xy plane. So we're going to have, basically we're extending, several of you asked as we were doing iterated integrals, why would we need to use an iterated integral to find an area in the plane? And we kind of don't really, because we already have tools to do that. So we're going to add something to our idea of multiple integration to give it a little more meaning. So we're going to say we have a surface z is some function of x, y, and is bounded by some region in the xy plane. And we want to find the volume of the solid that's formed by the boundaries of this region in the xy plane up to the surface. So underneath the surface, but inside this boundary in the xy plane. So we're going to draw a picture of what we're talking about. So here are our axes. And I also need to say we've been a little loose with our terminology, because I think several times we've talked about our multiple integrals, our iterated integrals, we've called them double integrals. And we haven't actually defined what a double integral is. So that's what we're going to do today, is define a double integral. We've just been using iterated integrals. So here's our surface up here above the xy plane. Some arbitrary surface up here. And this is z equals f of xy. And we have some region down here in the xy plane. And we want to find the volume bounded by this region that's underneath this surface. So what we're going to do is we're going to divide the region into small rectangles. So here's a little rectangle. Inside the region. And we're going to extend this up to the surface. So on the surface we're going to have some curved shape here. And we're going to find the volume of this little piece, and then we're going to sum the volumes of these little, if we make our division small enough, they're little rectangular prisms. We can approximate them by rectangular prisms. And then we're going to sum that over the region. So we're going to say the width of this prism is delta y sub I. And on this side it's delta x sub I. And their coordinates, the center of that is at x sub I and y sub I. So the volume of this little piece that we're talking about is going to be given by the area of the base times the height. The area of the base is just delta x sub I, delta y sub I. And we're going to call that delta A sub I. So we have this little increment of area in our region. And the height of each of these that are approximately rectangular prisms, the height is f of x sub I, y sub I. So our volume of a single one of these prisms is v sub I is f of x sub I, y sub I times delta A sub I. And the volume bounded by this solid inside this region is just going to be the sum of the volume of these little prisms over this entire region. So the total volume is going to be the sum for I equals 1 to n, however many little pieces we're dividing our region into, of f of x sub I, y sub I, delta A sub I.
So what was the thing that we were doing yesterday, like the example folded, like because that was the same thing where you had like a region above?
Right.
Was
So that's really what we're talking about today. We're going to give it a precise meaning today.
Okay, but it's a similar.
It's the same idea, right? And then what we're going to do is take the limit as delta x sub I and delta y sub I go to 0. And we're being a little loose with our definitions, with our terminology here. A couple of things just so that you know. In order for this to work, we need all of our little delta A sub i's. We need to be able to subdivide our region so that all the little delta A sub i's fall inside the region. Now that's going to happen anytime our boundary in the xy plane is nice functions. So anything we're going to talk about, this would hold. And I'm going to say that delta A sub I approaches 0. What is technically happening is we say the norm approaches 0, and the norm is the length of the longest diagonal of any of these delta A sub i's. We don't have to divide them into little squares. We're letting the length of the longest diagonal approach 0. So in essence, this little increment delta A sub I is approaching 0. I'm being a little loose with the symbols and the terminology. I just want you guys to be aware of that. So we'll take the limit as delta A sub I approaches 0. And that's going to be our total volume. And this is going to give us our definition of a double integral. So we're going to take the limit of this sum as delta A sub I approaches 0. This is how we're going to define a double integral. So before I switch the page, everybody understand what we've done here. It's a pretty not a difficult concept that we're working with. So we have this sum. We're taking the limit as delta A sub I approaches 0. That's going to be our volume underneath our surface bounded by this region in the xy plane. Yeah.
Why would you want to find the volume of the surface bounded by that region?
It's another tool to allow us to find volumes of solids. We're going to extend this, and this idea of volume is going to let us find centers of mass and moments of inertia very easily for a material where the density varies in terms of your position in the material. So that's just some application. But really what we want to do, we're interpreting this as a volume. What we're working towards is defining a double integral. And then we're going to use double integrals for other things as well. Okay? All right, so with this idea, we're going to take the limit as delta a sub I approaches 0. That's going to be our definition of a double integral. So we're going to define and we write this as the double integral over R of f sub x, y, dA. So this is a double integral. And this equals the limit as delta A approaches 0, and this is where I'm being loose with our symbols. The sum I equals 1 to n f x sub I, y sub I, delta a sub I. So this is the definition of a double integral, and it occurs when the limit exists. And our conditions R is a closed bounded region in the xy plane.
Like below
Below are two integral signs. So this is the double integral over R of f of xy dA. That's our definition of the double integral. And in this section, we're going to use the double integral to find the volume between the xy plane and this surface bounded by our region. So we're going to say that the volume below f of xy, bounded by this region, we're going to say the volume equals the double integral of R of f dA. And for this, we need f of xy greater than 0, and it needs to be continuous in R. So this is how we can interpret this double integral, is the volume below f bounded by the region R in the plane. So now we know what a double integral is. The double integral is this limit. That's how we're defining our double integral. Double integrals have properties very similar to single integrals. We can multiply by a constant. We can sum double integrals. We can take the difference of double integrals. I'm not going to list out all the properties. They're all familiar to us from doing regular single integration. If you want to look at them, they're in your book on page 992. So they're same properties as single integrals. The way we can manipulate them mirrors what we do with single integral. Page 992, they list properties of multiple integrals. You'll look at it and say, oh, this makes sense. The same thing we can do, same types of things we can do with single integrals. Sums, differences, multiplied by a constant, that kind of thing. All right, so now we have a definition. We need to know how to evaluate these. This definition doesn't tell us anything about how to evaluate a double integral. Well, we have a nice theorem that was proved by a gentleman by the name of Fubini. So Fubini's theorem tells us how we evaluate this double integral. And what would you guess Fubini's theorem tells us? What have we been doing in the last section? Iterated integrals. Fubini's theorem says we can evaluate a double integral as an iterated integral. So Fubini's theorem says that if we have our function, if x is continuous in a region, and we're going to talk about two different kinds of regions, our vertically simple region and our horizontally simple region. So if we have a less than or equal to x less than or equal to b, and g1 of x is less than or equal to y less than or equal to g2 of x, then our double integral of r of f of x y dA equals our iterated integral. Integral from a to b, integral g1 of x, g2 of x, f of xy, dy dx. And this is for our vertically simple region. And it's the same thing for a horizontally simple region. So basically Fubini's theorem tells us that we can evaluate a double integral as long as we have these conditions met, which is what we're going to have pretty much always, as an iterated integral. So our second condition is just for our horizontally simple region. C is less than or equal to y, d, then we just have our double integral is our iterated integral for a horizontally simple region. And our order here is reversed. Dx, dy. So now we have a geometric interpretation of this iterated integral where we have a function inside, and now we have a little bit more of a purpose for doing these iterated integrals because we want to find. Otherwise, we wouldn't be able to find this volume that we're interested in. And then we'll talk about this function f of xy as being other things other than the height above the xy plane, and give some interpretation to those types of double integrals. All right, so we have any questions on double integrals and what we're doing with them? All right, so let's get to the fun part, actually doing some double integrals. So what I want to do is just do several examples of setting up double integrals and talking about our regions and that kind of thing. That's really the difficulty with multiple integration is not necessarily the integration. We're all pretty good at that. The difficulty usually comes from figuring out what the region is and setting up the limits of integration properly. That's really where the challenge tends to be with double integration. All right, so let's look at so we're going to evaluate this double integral. We want to set up For this one, we're just going to set up for both orders of integration. So we want to set up for both orders. And our region is bounded by y equals 0, y equals square root of x, and x equals 4. So often your problem will be set up this way. It'll give you this double integral that you're supposed to evaluate and just tell you what your region is. What I'm going to suggest, what I always do when I do these, is one, I sketch the region in the xy plane to help me visualize how to set up my limits. So as a step in setting these up, I would suggest sketching the region in the xy plane. It doesn't have to be a beautiful sketch. It doesn't have to be an accurate graph. It's just enough to give you an idea of where the region is. So we're bounded by y equals 0. Well, y equals 0 is the x-axis. There's y equals square root of x. And by x equals 4. So there's x equals 4. So our region is inside there. So we want to set this up for both orders of integration. So let's do a vertically simple region first. So for the vertically simple region, our outer integral is going to be for dx. So what are our x variables of integration going to be here? 0 to 4. Y. 0 to square root of x. So if it helps, you can draw your little rectangle in here. So I'm going to draw my rectangle. If I'm going this way, y goes from 0 up to my function, 0 to square root of x. And then we have y over 1 plus x squared dy dx. So that's the first order of integration. And this one, is this one going to be an easy one, easy integral to evaluate, or a difficult integral to evaluate? This one's not too bad, because we have a y here, so that's going to evaluate pretty easily. This one's pretty easy. We would have, let's see, square root of x.
No, the x squared on the bottom.
Right, the x squared on the bottom, so we just have, right. Mm-hmm. All right, and then let's set up our horizontal rectangles. So for the horizontal, our horizontal rectangle, y is going to go from, or sorry, x is going to go from, actually we need y. So what's y here? 2. Y equals 2. So y is going to go from 0 to 2, and x is going to go from, let's be careful with this one, y squared to 4. There we go. Because we're going this way, so we go from the function to there, y squared to 4, y over 1 plus x squared dx dy. And this one will be a more difficult integral to evaluate for the first iteration. So this one's easy. Or sorry, this one is difficult. So remember, when we do the inner integral here, we're integrating with respect to x. For inverse tangent, do we need, is it 1 over? Yeah, so we have an inverse tangent. And then, so I would choose to evaluate this one just because it turns out a little easier. So there's our setup, and we can evaluate these. So questions on that one? Okay, let's do another example. We want to find the volume volume below x plus y plus z equals 2, above the first octants. So we need to figure out our region here. Let's draw a little sketch. So what kind of surface is this? This is going to be a plane. And if we write our surface as z equals f of x, y, this would be z equals 2 minus x minus y. So that would be our function. How are we going to figure out our boundaries, our region in the xy plane? We could solve for when z is 0. Let's go even further. How would we graph this plane? Find the intercepts. So when x and y equals 0, z equals 2. So we have z equals 2 up here. When x and z equals 0, y equals 2, and when z and y and z are 0, we have our intercepts. So our intersection with the first octant looks like this. So we're finding the volume of this kind of triangular shape, pyramid shape. So we need our region in the xy plane. On the xy plane, our region looks like this. So we need the equation of this line. So what would be the equation of this line? Z equals 0, so this would be x plus y equals 2. So we could say that we can use this to find our x limit or our y limit. So now we're ready to set up our double integral. So we're going to find the volume. Our volume is going to be a double integral, I'll leave my limits off for now, of 2 minus x minus y. And let's set up our vertical rectangles first. So if I set my rectangles this way, our inner integral y is going to go from 0 to what? 2 minus x. And x is going to vary from 0 to 2, dy dx. And if I do the horizontal rectangle, so this is vertical, x is going to go from 0 to 2 minus y, and y is going to go from 0 to 2. Either one of these is not too bad to evaluate. We just have polynomials here. So either one of these would be, we could choose to evaluate either one of these. Questions on how we set that one up? So again, defining our region in the xy plane is often a challenge. Let's look at one more, and then I have a couple questions for you. So for this one, we're going to start with our region. We're going to start with a drawing. and come up with our double integral for the volume from our drawing. So this is a segment of y equals x. This is a segment of y equals 2. And this is z equals 4 minus y squared. And we want to find our volume here, below this surface bounded by this region. So let's sketch our region in the xy plane. So here's our line y equals x, and here's the line y equals 2. So where is our region, to the left or to the right here? Our region is here when we're looking at it from above, so it's going to be to the left. So that's going to be our region. So let's set up our vertical rectangles. So we have integral, and it can be helpful to set them up inside out if it helps you think that way. 4 minus y squared, and we're going to do dy dx. So y here is going to vary from what to what in our region? X to 2, because this is y equals 2 here. And x is going to vary from 0 to 2. So this is going to be 0 to 2. So our volume is given by that integral. If we do horizontal, our volume is going to be given by this double integral. So in our region, x varies from what to what? We're here, so 0 to y. And then y varies from 0 to 2. And either one of these integrals not too difficult to do. Now personally, and this is just my personal choice, I always try to set up vertical rectangles first. That's just my personal bias, is to set up vertical rectangles. Whenever I think of a double integral, I think dy dx. That's just my first thought. It's not necessary to do it that way. I just have an easier time visualizing in that order. But you can set them up in whatever order is going to be easiest to work with. If one looks difficult, set it up in the other order and see if that helps you with your evaluation. All right, any questions on setting these up? Not really much different than what we did before. We're just adding a function in there. All right, I have a couple questions for you now. We're going to say so R is some county in the USA. And we're going to say this function f of xy is the total snowfall at some point xy in R. So in our county. My first question, what is this? What would that, how would we interpret that, given this? The volume of the snow? And what do we call the volume of snow that falls on some place? The volume of snow, that's the total snowfall, right? What's that?
What do they do by height?
Not anymore.
The height? The height?
That's why it's total snowfall, how is the region
I guess the volume of the snow would be the most accurate way to say it. So that you'd say on this county 6 inches of snow fell, so you'd have the volume of the snow, right? So this would be the volume. Don't you think that would be a better measure of the total snowfall, the volume of the snow?
Tell us how much more.
Yeah.
Well, maybe they use it. And we go for that in cubic feet. Go 5.
Yeah, that would be good. All right. So what would this be? What would that be? So what did we decide this top one was? That's the volume. What's the double integral of dA over a region?
Volume of the cap, that's the area of the cap.
That would be the area. So this would be the volume per area.
That's 10 units.
So maybe that would be the way to decide if there's a snow day. If you get a certain volume per unit area of snow, then you have to cancel school. Right?
Are we one of the, I was one
Shove it all into like 1 cubic.
Yeah, no, kids use round thumbs like a giant ruler and now they're like,
All right, one other question, and then we'll stop. So I want to find the volume here. I want to find the volume of this solid. What would be the easiest way to do this? So yeah, this one I could do a double integral here, right? Here's my surface, z equals 4x, and I have my region in the xy plane. I could set up a double integral, but yeah, Lee says use geometry. Garrett says it's a rectangular prism, divide it in half. Okay. Often, if you get a region like this, people will set up the double integral and evaluate it to find the volume, which is fine. But if you can figure out some shortcuts, use some shortcuts.
So on your test, if we find the region like this is okay, we just say use geometry.
It depends. It depends on what the question asks. If the question asks find the volume of the solid by setting up and evaluating a double integral, then not. But if it just says find the volume of the solid, then you could say the volume of a whatever. Yeah, use geometry. Yeah. That's the height. That's the height of the.
Does that matter if you take the double integral?
No, because that would come out of your limits. Your limits of integration would take care of that.
Okay.
Okay? All right, any questions? All right, homework. All right, there you go.